Dr. Harshavardhan? Is his audio not working?
Yes. So you can disconnect and rejoin again.
You are not audible, sir. Dr. Harsha, you are not audible. You are not audible, Doctor. You can just call him, Rui, and tell him.
Yes.
Because it seems he is unable to hear us also. Dr. Harsha, you are not audible.
I think Ruhi, you should call him up and ask him, you know, like.
Yeah, she is calling him.
Yeah.
Yeah, he's joining from phone also.
Okay, fine.
For audio.
Audience, please bear with us for this technical hitch.
Yeah, you should be able to hear me now. So what I'll do is I'll use the phone for audio and sorry, the Prime Minister held me up. I was more than 40 minutes in traffic, just sitting tight. Let's start. We're ready to start. I'm ready to go.
Welcome, Dr. Harsha.
Thanks, Vinay.
Welcome, sir.
Sorry for giving you so much
No problem, no problem.
Thanks for bearing with me.
Thank you.
We should start here.
There is an echo, I think.
Yes.
Yeah, because you are on two equipments.
There shouldn't be an echo.
Now it is not there.
Yes. Now it's not there.
But your screen is not. Your screen is not full. I don't know how it's going to be a presentation. Larger.
And you can turn out the video from the mobile, the second connection from where you are connected audio. Because
How do I do that?
you can just turn off the video, right? Yeah, that's yeah.
Okay.
Yeah, that would be better.
And we'll use this for video. Right?
Yes.
Let's go.
Yes. Let's start. Go ahead, Rui.
Yes, ma'am. Good evening, everyone. I welcome you all for our 6 months webinar series on steel bridges, day 5, sponsored by JSW Steel Limited. Today we have Dr. Harshavardhan Subbarao. He will be speaking on the steel bridge advantages and design and construction of 4.4 meter long DIGHA-SONPUR rail cum road bridges, BIHAR. Before we start, I would like to play a small introductory video of IIBG. Now I request Madam Purnima to play introductory video of JSW Steel Limited.
India, a nation powered by 1 billion dreams. Dreams that we aspire to fulfill every day. Together with our collaboration and commitment, as India embraces to be a $5 trillion economy by 2025, we are all geared up to be a part of this monumental journey to usher in a brighter, better future. Together, we touch ordinary lives and make that difference. We better every day. Together, we make steel that you carve into your agri-equipment. Together, we sow the seeds of success. We make steel that gives the grit and grind to your heavy equipment. Together, we change the landscape of our country. We make steel that you beautifully mold into your automobiles, just to drive our nation on its path towards prosperity. We make steel that you transform into solar energy. Together, we steer our nation towards a greener tomorrow. We make steel that relays your transmission lines, just to brighten the future of millions. We make steel that styles your appliances. Together, we bring happy smiles. We make steel that adorns your development projects. Together, we provide shelter to millions. We touch lives, make them better together, every day. We empower communities, make them better together, every day. We nurture dreams, make them better together, every day. As India embarks on its accelerated growth journey, we are firmly placed to leave our mark in it. Together, we touch millions of lives. and make them better every day.
Thank you. Now, I would like to hand over the session to our today's moderator, Dr. Jyoti Busari, our Executive Committee member. Over to you, ma'am. Thank you. Ma'am, you are muted.
Thank you, Rui. Are you going to share the slide, introductory slides? Yeah, please. So I welcome all the participants for this 6 months webinar series on the steel bridges, the day 5th. Actually, just one more to go to end up this series. And today's speaker is Dr. Harshavardhan Subbarao, Chairman and Managing Director, Consumer Consultancy Private Limited. Dr. Harshavardhan Subbarao, he holds a PhD in steel structures from Imperial College, London, and MS Engineering from University of Michigan. He has been designer of number of landmark award-winning projects such as Signature Cable Stayed Bridge, Delhi, 4.56 kilometer rail cum road bridge, Patna, bridge number 20 on JURL metros, viaducts, elevated roads, cable stayed arch, and extradoors bridges, underpasses, etc. He is Vice President of IABSE Zurich and member of its technical committee and past chair of its bulletin edit board, and serves on several committees of IRC, BIS, IABSE, and FIB, Highway Research Board of India, and various international and national bodies. He is the member of BIS Apex Committee, CED 7 for steel structures and sections, was a committee member of IS 800 Limit State Code 2 and co-convener of IRC Steel and Composite Bridge Committee. He has over 30 years of experience and serves on various international and national scientific and technical committees, electoral boards, and has number of papers and publication bridge projects to his credit. Today he will be speaking on the steel bridge advantages and the design and construction of the 4.4 kilometer DIGHA-SONPUR rail cum road bridge, Bihar. This DIGHA-SONPUR rail bridge road, it is across the river Ganga, connecting the Digha Ghat in Patna and the Pahlej Ghat in Sonpur, Bihar. Right? It's a steel truss bridge, also called as JP Setu. So this bridge, I think it is the second largest rail cum road bridge in India after the Bogeybill Bridge in Assam. So let's try to understand the steel bridge advantages, and let's hear the experiences from Dr. Harsha related with the design and construction of this wonderful bridge of DIGHA-SONPUR rail cum road bridge, Bihar. Over to you, Harsha.
Thank you, ma'am. I want to share the screen. So
yeah,
I'm just wondering how I'll do that.
You're on the laptop, right?
Yeah, if I can just minimize. Just give me a minute and able to get the open.
So you have to just click the share screen icon.
Yeah, green button is there.
Is it showing now?
Not yet. Yeah, it started. Yes.
Wonderful. Good afternoon, all. Rather good evening. I was late in joining, so I apologize. That was our Prime Minister on the road, and he held me back by reaching you by 40 minutes. So on that note, I want to talk to you today about quite an achievement of mine, something which I'm very proud about as a bridge designer. In fact, it's as significant as the design of Signature Bridge, Cable Stayed Bridge in Delhi. And this is the Patna Rail cum Road Bridge, which also is in steel, just like the Signature Bridge Delhi. It's a steel and steel composite structure. Similarly, here we're going to talk about trusses today, 36 trusses of 123 meters each built over the Ganga at Patna. And I'm going to talk to you about that today. And if there is time, I will move ahead and speak about the other part which I want to talk about is the advantages of building in steel. Okay, so if I can come to that, I will start. So it is the longest riveted truss rail cum road bridge. Bogeybill is a welded, and this was the last of those long riveted steel bridges. And it is also the third longest bridge in India, they say, on a river. And I want to come to the topics straight away. The stakeholders, the Indian Railway, the contractors IRCON, us as the design consultants, my company. We were also the erection supervision consultants for the entire project. The subcontractors, GPT, Rahi, and Tante Constructions for IRCON, one on each bank. The erection design consultants for the erection schemes was TUP from Kolkata and CDC from Kolkata. And the proof checking of all those erection schemes was again done by CCPL customer us. So this was the project. And as you know, there are a number of lovely bridges that are built. You see here this second Hooghly Bridge, which is also in steel with ladder deck construction. Steel is, been around in India for quite a long time in advanced construction and also in various other kinds of bridges. This bridge, for example, is a 2 into 154 meter span. What you see in brown in front is the launching nose. There were two spans stitched together of 154 meters. On one side, there's a tunnel. We had a little space. We stitched both these and push launched it across this 90-meter slip-formed pier, which you see in the middle in Seismic Zone 5 in Jammu and the Jammu-Udhampur-Katra rail link. And we pushed this across all the way into a tunnel on the other side. So it was another extremely challenging job. And this span's actually held the world record for a truss span for nearly 20 years since it was built. It was only 3 years ago that we came to know that the Chinese have built an exactly 2 into 156 meter span. Otherwise, this was a Guinness Book of World Records achievement. There you see the complete bridge. Then coming down to something like Signature Bridge, whose pylon is again in steel, a beautiful, reflecting the aspirations of modern India with the Namaste symbol and so on. There's lots have been spoken about it. And, I was very proud to be involved with its design and its development, and seeing it through till the end was a particular joy. The cable stay bridge, of course, has a different type of behavior than the one that we are going to discuss today. But I thought I should tell you about where we are going a little ahead. It's probably our most technologically advanced bridge in India. So brief about our particular bridge, the Patna Rail Cum Road Bridge. It was originally a rail bridge. Then the National Highway Authority asked the railway for converting it to a rail cum road bridge. So a rail-only bridge with a single track of rail was converted into a rail cum road bridge at the behest of National Highway Authority. That was because the adjacent upstream, the old Patna rail, the Patna road bridge was in very bad shape, and vehicles were unable to get across easily. With great difficulty, they used to cross. And so it was decided that to convert this as an interim measure into a rail cum road bridge with 2 lanes of national highway in the middle, and in the middle level of the truss, and in the bottom floor level of the truss to have 2 broad gauge rails. So then we were awarded this task of finding out if this change can be done. After all, the foundations and substructure had already been done by HCC. They were already in the ground. And we needed to find out then, can the additional load be taken? Can the seismic actions that will now accrue be, because we introduce a huge concrete mass in the middle, a simple truss, with bottom and top chord now has an intermediate floor level with a high mass, as high seismic agitated mass of concrete for the road deck. So we needed to check whether the foundations were good enough, the double D foundations, whether the substructure was good enough in terms of hinging, in terms of its ability, in terms of its design to withstand this additional new loading, which the road deck would impose upon it, and the one additional DG line that was requested we put also onto this. So this was our brief. We first checked the substructure. We checked that there was supreme reserve in this foundation and substructures, and we were very much happy about that, and decided to go for this railway plus road bridge in this same alignment on the already built foundation and substructures. We found that the adequacy of the foundations were clearly there. We found that we can go ahead, and we were awarded then the full design and analysis of the superstructure. Then we were appointed thereafter, not only for the superstructure, but we were appointed proof checking consultant for the entire erection and also to construction supervision of the entire launching of 36 plus 2 spans of 64 over the Ganga, 36 into 123, and 2 into 64, the end makeup span, which I'll show you about. The location joining two national highways on each side, spanning from DIGHA on the one bank to Sonpur on the other bank, going through some sort of a sandy stretches on the Ganga, which we take advantage of. And the crossing actually is very strategic, is joining two national highways on either side. You can see below the national highway lines being shown in yellow, being joined by the road deck, and the rail, which joins then two strategic locations. You can see here on the right side photograph, the already built bridge. It's already existent alignment. You can see the bridge that goes, how it spans from one end to the other. In fact, if you stand on the shore at one end, you don't see the other end. It is so long, it's over the curve of the horizon, more or less. So here you see the road deck, and the rail has a different aspect, which you can see in the bottom right, the rail being on the lower embankment, the road being at the higher deck, and both integrating in and crossing the river. You see this here very clearly. So that's the sort of general alignment that we had, and the location and so on. Palej Ghat being shown there. And to give you an idea, those are the two end makeup spans of 63, and joining NH19 on that side, NH98 on this side, and the Chapra Hajipur line on that side of the Ganga, the railway line on that side of the Ganga, and the main railway line on this side of the Ganga, Delhi, Mughal Sarai, Howrah, etc. So it was very strategic to join both these across the Ganga, both from a rail's point of view and desperately required for vehicular traffic, because the Ganga bridge at Patna, the MG Setu, was in very bad shape, and this could provide relief. So you see on the right, the concept that was initially evolved, and then how we went about going with a span arrangement of 123 and 119.6. Today, I'll be speaking to you about the larger span, not the smaller span. Maybe on another occasion, I'll speak to you about the smaller span. It's not that exciting. And you see here the depths of the foundations, etc., 40 meter, 45 meter deep from foundations. The plan at the rail deck, initially as it was conceived, I'm showing you, was only for one railway track. And these are all from railways' earlier records, for which the foundations were already built, the double D well foundations with these piers, which I'll show you. And this was the plan at the rail deck. This is all it was for. We had to requalify the whole structure to take on the road deck, which you see here, plan at the road deck, with expansion joints exactly in line with the 123 meter truss for the rail. So the expansion joints were kept the same. So 2 tracks and 2 lanes. So far, it's the longest span truss railway bridge, 2 into 154, which were earlier constructed and was in place and operational on the Jammu-Udhampur rail link, yet to become operational at that time, was already done by us, and we had done that in 3D. And that experience helped us a lot and gave us a lot of confidence in this design. The steel truss is an end diamond type arrangement, slightly modified end diamond type arrangement, I would say, with 16 panels of 7.45 approximately, and height between the centers of the bottom chord and the top chord of the truss of 18.25 meters, and a width between of 10.925 meters. All the bottom chords and first and last diagonals of the truss are box sections, because we wanted their torsional ability and we wanted their strength. And then the rest of the sections are I sections, including all the cross girders, including the end cross girders, so that we can facilitate joining to the top and bottom chords, which are box sections. The I section frames very easily into a gusset at that location. A box on box is very much more difficult to frame. So a box on box connection. So bearings are pot PTFE. The detailed design of the superstructure, the loadings that we considered, the permanent loads, dead load, superimposed loads, live loads, railway live load, railway road live load, the pedestrian live load, and the gangway live load for when there are gangways on which the railway, at the railway level, the gangway, their live loads for people and equipment that they take on those gangways. Then the incidental live loads, of course, wind, seismics, and effects of temperature, being a steel truss of a large length. Earlier railway trusses are analyzed as pin jointed in 2D, but because in 154 meter span of bridge 20, we had done a full 3D FE analysis with space beam elements, 6-degree independent degree of freedom space beam elements. We were very much confident, and we went for a full 3D analysis here too. And it is correct that it is not pin jointed. Hitherto, everything was being designed as pin jointed 20 years back or so in the railways, a pin jointed behavior at each joint. But the gusset is very rigid. The number of rivets or bolts that come into a gusset make it extremely rigid, and it lends a beyond partial fixity, almost full fixity at that joint. So it is justified to use not a truss element, but to use a space beam element with 6 degrees of freedom at each node. And that is how we went about the entire project. Because this is actually the truth. When the gussets are so huge, they're taller than me. Some of the gussets are huge. So there is obviously fixity, and we treat it as a rigid jointed truss, not as a pin jointed truss. And that's why we did the space frame analysis for the whole structure of 123 meters. They are simple support. Each span, the spans are not continuous in that sense. They're simple support spanning 123 meters between two piers. Now, wherever the joints were there at the rail level, the same joints were carried up into the road level 2, which is at the mid level of the truss. All the joints are riveted with HTS, high tensile steel. The bottom, top chord, first and last diamonds, diamonds in the sense the last diagonal, the end location of the face of the truss, the last diamond of the face of the truss, are box sections because we need their robustness, their rigidity, and their very strong resistance to buckling characteristics. And because all the load path there goes down into at the ends, of course, the whole load path goes down while the end portals into the bearings. So we needed that zone at the ends of the truss to be very, very robust, which we did in box section. Adequate access holes for entry of a person inside for riveting and also future inspection, which I'll show you. This was a particular innovation, a particular feature of this job. All other diagonals and cross girders were made of I sections. Each member is designed as per the IRS steel bridge code. Checking was also done for local buckling, a unique feature for the first time probably in the history of Indian Railways, that local buckling phenomena, where when you put compression into plate, it buckles in the form of waves in compression buckling. For axial compression along with bending, since it was a very high D by T, we needed to have very deep boxes, so the webs of the boxes became susceptible to buckling under a certain circumstance of launching, which I'll discuss with you later. And of course, the whole design is an allowable stress elastic design, which was in vogue at that time in the IRS code. So the entire truss is designed with working stress and allowable stress type approach, permissible stress type approach. And we made an attempt to keep the utilization ratios of all the members in whatever condition, whether it's prone to buckling or yielding, and designing them as compact to plastic. We are trying to keep the stress ratios around 0.8 as far as possible, and keep some reserve of at least 20% in this truss for the future events, especially since it was designed for MBG loading, but it probably can take 25.5 ton axial loading as well of the railways. Now, provision of pre-camber, this is very much important because when we're launching, there is only the steel, and there is nothing more than that. And when we are launching the truss, to counteract the deflection, we need to consider only the steel when we're launching. There is no concrete yet in place. Then when there is, with the dead load plus SIDL is added, the concrete deck is put and the crash barriers, etc., and all that, and all the stuff is done. Then, of course, live load flies. So to counteract the deflection due to dead load plus live load in the final condition, when the truss will become flat under live load movement of the train, especially, and the road, it will become flat. Then it goes back to a hug-up condition of camber, and that is camber to counteract these deflections which accrue over time. And there is relaxation in the joints, and then you get a permanent set of deflection over time to guard against that, and to also guard against secondary stresses that happen because, for example, neutral axis of members framing at a joint are not in the same working point. They are up and down. The members' neutral axis will be different. Cross members' neutral axis, main members' neutral axis may be different, and will create secondary moments. So those secondary effects, to counter all that, we resort to giving camber, which is a very important requirement of such a long truss, and getting it right is very, very important. So the arrangement of permanent bearings, horizontal bearing reaction became more than 25% of the vertical reaction. Therefore, as per the IRC 83 code at that time, the railways asked us to then separate both the bearings, and this was for the first time we have separated both the bearings and 40 TP bearings separately to take vertical and separately to take horizontal, which I'll show you. This required the bearings to be separated, of course. So horizontal longitudinal force bearings placed below the extended part of the bottom chord. So the bottom chord is projected beyond the bearing, and there is where we place the longitudinal force bearings. and the transverse horizontal bearings are put in the end cross girder to arrest the transverse, say, seismic action. So this way, there was no bending in the truss in the plane of the paper, in plane of paper, due to the effect of an earthquake or due to any braking actions. Now, there would be no in-plane bending of the truss. So this was a very important innovation and concept so that we could prevent any out-of-plane buckling of the truss, out-of-plane movement or buckling of the truss by this clever arrangement of the bearings, which I'll discuss with you. I'm not sure something is not right here. Just give me a minute. I'm having a little stuck. I'm not able to see the titles. So the arrangement of the permanent bearings, as I told you, we did that to prevent any bending that would happen, and only bending, especially during the earthquake. There would be no bending out of plane during an earthquake. Only the longitudinal force would be taken in the longitudinal direction, and the transverse force would be taken on the transverse direction by those bearings and those these things that we talk about. I'm having some difficulty, ma'am, in that I'm not able to fit this typically to the screen. Can anybody help me? You know, it's not fitting exactly to the screen.
So you can do the full screen.
I have, ma'am. One second, let me just go back. And right. So again, I'm having something at the top which is affecting the titles.
Okay,
It's
I'm
not-
just trying to remove this.
Let me do something. Is that okay now?
Yes,
Okay.
we can see the screen clearly, sir.
There's no other disturbance to your screen, right? Nothing.
Yes, yes. No disturb, nothing.
Now, the horizontal force is, of course, transferred from the bearing to the pedestal, from the pedestal to the pier cap. Here, the problem was because it was designed already for that simple one railway line and no road, there was inadequate dowel bars in the pedestal to take the shearing action and in the existing pier caps that were already done. So what we did, the pedestals that were very small and so on, we required to innovate, and we used a Hilti system to improvise on this, and I'll talk to you about that, where in each pier cap, 183 additional Hilti bars were installed, and the existing pedestals were all integrated, and a huge sort of beam type pedestal was made, and I will explain that to you in the next few slides. Okay. Again, I'm having a problem, ma'am, in advancing these slides. Okay, now part B of this, which we had been assigned, as the second part of our scope of work, was the proof checking of the already constructed well foundation of structures and pedestals to check their adequacy for this increased rail plus a new full bridge deck, bridge deck we were putting in the middle. So I discussed that to you later, and I'll tell you about the unique arrangement that we made and how whilst everything was okay, the pedestals were inadequate, and especially for seismic shear and for the restrainers, we innovated quite an amazing thing, which I'll share with you in the next few slides. So part C of our assignment was the proof checking of the erection scheme of the superstructure. Each contractor had their own specialist consultant on each side, which provided different schemes somewhat. And we had to be doubly sure that over the Ganga, launching 24 hours, 365 days a year, there would be no untoward incident when we're about 60, 70 meters, 50 meters over the Ganga River at all times. So this method of erection was one in which the anchor span is first done. It is used as a ballast, and some tie elements are put between this existing anchor span on staging on each shore, construct on each shore, which serves as a ballasting span, and we connect it and with the link element system, and we then start forward cantilevering from pier 1 to pier 2 in the free air from 123 meters all the way across the Ganges. From pier 1 to pier 2, we triangulate and build up the structure with an overhead crane, and I will show you how that is done. Of course, it is very important to have the camber, as I discussed, and that camber has to be designed in and ensured during erection. Okay, so there were many contributions we made as a proof consultant especially on the erection. What happened was, because of the compression buckling, we had to increase the grade of the concrete to E590, 590E from what was a 350 grade or 250 grade, the normal grade that we were using. We had to increase the grade from 490 to 590E, a huge increase in the yield stress, and also the thickness of the lower elements, lower chord elements between the two nodes, L0, L1, and L1, L2, and similarly in the uppermost chord, upper chord, and then there's a middle level, of course, for the road deck. And the uppermost chord, U1 to U3, we had to change the grade of the steel to HT steel from what it was designed, just because of the erection requirements. Of course, you can imagine why you need that. That is because the bridge will tend to sag when it is in its fully built condition and in service. But during erection, it will be hogging. The bottom chord will come into compression, and when it's at maximum cantilever before it touches the other side, you have the maximum bending, downward sag bending, putting in plane compression and bending compression, which cumulatively grows due to the weight. And at L0 node and at U1 node on top, you get the counteractive couple, contrary to what should be in the normal design. And you get a huge amount of compression accruing at the bottom, for which, to get balance that Z, you have to also act at the top, Z, of course, being I by Y. You have to also act at the top, and we had to jump up the grades for these three critical nodes, say 15 meters length in bottom and top. We had to increase the grade and also increase the web thicknesses, which were prone to compression buckling as plate elements. So this is one. And of course, then the contractor wanted to only use a buffer slab in between the face of the two edge girder, the bottom booms, bottom cords. But we asked for temporary bearings below those bottom cords to increase the safety, and you'll see why this was so important in the project. I'll show you why it became so important in the slides that I start showing you, photographs I start showing you soon. So temporary erection, so this was done, and buffer blocks noted that the thickness would not be adequate. You see, the buffer blocks would be subjected to huge compression, and the kind of metal and the kind of grade of metal and that they would simply have crushed. So we had to, as an erection consultant, we had to do detailed FEA to strengthen those solid buffer blocks at the bottom, solid steel, curved steel buffer blocks at the bottom. We had to do that with detailed FE analysis. So I will now tell you about the design criteria for a 123 meter span. It is in three parts: the loads, the permissible stress. Mind you, it's a working stress elastic design. A permissible stress is design, if you so call it. And what are the various lists of codes for a bridge like this? A typical loads, you have, it is MDG loading, and you have bending moment, shear, and CDA. DA is the dynamic augmentation for railway. So for a main truss, two nodes are so far apart, and this the bending moment per span, and so on and so forth. These are the loads that are coming, and so on. And so we develop a design criteria for the design of all the elements in bending, shear, and whether they are subjected to dynamic augmentation, that is something like our impact factor for road bridges, dynamic augmentation or otherwise, okay, and what the multiplier should be for the CDA, for the dynamic augmentation for each of the members, and what should be the length to be considered for each of the members. All those things are laid down in loading, and for the road deck also, it is from IRC, the road deck, of course, 2 lanes of 170R or 2 of Class A, etc., and where it will be positioned. All that is laid down in the design criteria, and the deck slab, the dead load to how thick, etc. All those things are laid down, the cross girders, everything, the wind that has to be considered, the seismic loading of 0.12 G. Incidentally, 0.12 G came from a site-specific study. We had earlier designed Munger Bridge. So 3 bridges, Munger, Patna, and Bogibeel, had very high quality site-specific seismic studies done. And when we designed Munger, which had 125 meters span, 2.6 kilometers long, at that time, it was realized that site-specific seismic study must be done for these three important bridges, and a jumped-up factor of 0.12 G is the design requirement based upon a site-specific seismic study for this location. And in fact, for all three locations, we were given higher values to design for. So this is the, there are certain, the bridge rules, the IRS in railway have a document called the bridge rules, which lays down all the loadings, etc., and all that for the railway part. For the road part, we take from the IRC 6. And then, of course, there are some overriding clauses when seismic is considered. For example, horizontal seismic force due to live load on the bridge will be ignored when acting in the direction of traffic. But when acting in the direction perpendicular traffic, 50% of the design live load without impact shall be considered for seismic mass. So there are some overriding clauses which we have to cleverly take. And since it is largely dominated by behavior under live load of a train, the live load by road and the road deck is trivial compared to the railway loading as such. So we, of course, biased that clause, and we have to accept that clause and utilize that kind of combination. So then you have temperature, you have the derailment load, which was not considered in this project, density of steel, all these things are laid down typically, where to put the jacking, etc. What should be the girder deflection should be limited to L by 600. All that is laid down, and then for the composite bridge deck, what should be the strength and the yield strengths and so on and so forth, and where the stringer should be, and they should be the primary phase for what, and in the secondary phase when they're made composite, what loads they should be designed for, what should be the long-term modular ratio, what should be the creep and shrinkage that we had to consider, the shrinkage especially for concrete, and so on. So all that is laid down in a typical design criteria like this. And here you have, in railway to understand, unlike us running our train of vehicles across in the analytical software, we use CAD Pro, Midas, whatever. In the railway, it is made simple. We convert the particular train which is under consideration, like a MBG loading or a 25.5 ton axle loading. They have different classes of loading like that. We convert them into an equivalent uniformly smeared distributed UD. It's made very simple. And the bridge rules lays down that. And we simply have to take that and multiply it by the impact factor, like what you see, the CDA. And then we consider the tractive effort and braking effort, etc., which vary with the length. So you see from 1 to 130, the total load for bending moment, what should be taken. And when we know the L and we know the nodal distance, etc., we get a table and we are able to immediately pick from this table what values, you see. So the equivalent, so it is very simple to convert the tractive, the braking force, etc., which are particular to railway, into a simple design table like this, and to also consider the loading in the form of an equivalent UDL for that particular train based upon the bridge route. So it becomes a very simplified approach to the live loading consideration, and the impact factor is directly considered based upon the length of the member under consideration for which impact is being considered. Similarly, in part B, that is on the action side. Then, of course, there's the allowable side, the basic permissible stress in steel. Whatever stresses should be for mild steel, IS 2062, and high yield steel, IS 857. This was before 2062, the railway side, 490B. So you can see the kind of sorry. Right. So you can see that the kind of permissible stresses in tension, in bending, for plates, for different elements, in shear, the permissible values, we cannot be exceeded. Okay, and this is also now declared by us in our design note based upon the LD by R, the fatigue, so on and so forth. We take it from the bridge rules. Then similarly, the rivets, if they're in mild steel or in high tensile steel, the code to which it is and what it should be, etc., in axial tension, shear, and bending, what should be the allowable stress in the rivet, and whether they are shop power driven shop rivets or field rivets, etc., that values, of course, for field rivets will be much less. So now the L by R effect on compression members, because of course it's a cord, compression, bending, truss-like behavior with some bending is bound to be there, and what are the permissible increase in stresses? When we consider secondary stresses, we're allowed to increase or wind or intermittent stresses, actions like wind or seismic, rare events like seismic. We're allowed to increase the with secondary stresses by 1.33, for example. Okay, when we consider the secondary stresses, which we have done because of the nature of our analysis also. So that is the provision. Now, workmanship, there are rules for workmanship and so on. A list of the various codes to which you design a railway bridge. Any railway bridge has its own codes, but the main codes are, of course, the steel bridge code. It's like your IRC 112 for concrete bridges or your IRC 24 for steel bridges, the mother code. And the bridge rules, which is similar to your IRC 6 for the loading consideration, the allowable stresses, etc. Then the schedule of dimensions, the moving dimension, very important. You have to you have to clear the moving dimension envelope for that particular train and that particular form of loading. It is declared, you cannot ever infringe into it with any of your structural pieces or members. So that, and similarly, the welding, it follows their welded bridge code, the welding requirements, the fabrication, and the follows their requirement, and so does the code of practice for welding, riveting, and the English bridge manual at site. The road, I think many of you would know, we have so many of our standard, this one, and the bearings, of course, were done to IRC 83 for the whole bridge. The 40 was designed based on IRC 83. So that's the other elements such as your welding, your oxygen clean, your radiography, how it should be done, so on and so forth. So many things are covered there. And then your IS 8093 for earthquake resistant design, 2062 for that. Then the concrete of the bridge deck, what all code compliances are required for the various elements, etc. And the various special publications of IRC, etc. of IS also. They are all listed and given state. And then the order of preference for international codes, in case we don't have our codes to cater for that, then the order of precedence to adopt international codes, all that is clearly stated in the design criteria. So what I showed you is an example of what a design criteria should be, how important it is to have it in a project before you start, get it agreed by the owners, the contractors, if they're already upon everyone, and that will now guide us for the complete design of the project. Okay, this is what I want to tell you about the design criteria for a bridge such as this, how you do it, what you lay down, and how it is structured. Now, the general arrangement of the 123 meter span, you see at the top here, can you see my pointer, or is it not visible?
It's visible. The pointer is visible. Go ahead.
Yes. It is visible.
It is visible.
My arrow is visible. Okay.
Yes,
so
yes.
The truss, the face of the truss, as I look at it broadside on along the length, L0, L1, L2 up to L16 are the nodes at the bottom. 7.6 or 8 or whatever I said between each node. Okay, and at the middle level is the road deck, and that is the M level, and U is the upper. And of course, you see here an incline here. This member, the last member is inclined, and this is a very, very important member. I will explain to you again later in the this thing why that is so. And you can see here the various types of members, the shapes and the dimensions are all laid down. And it is then very easy to imagine the sizing of these members. And you can see the diagonals between M0 and U1. M0 here and U1 is a box with a hat-like thing on the outside, has a little hat. It has a projected top. The entire outside of the truss, the entire outside, I mean the entire periphery of the truss has a hatting like this with 950. Okay, you can see that up to here. Then the bottom chord doesn't have that, of course, but the bottom chord is 1.4 meters nearly tall. You can almost walk inside it. And similarly, you see all the top chords are nearly 1 meter high inside them. And this is important to be able to do the riveting inside the box. That is very important to go inside the box and inspect the box and check the inside of the box at future time. So the diagonals are again boxes at certain locations, and all the other locations, that is this end diamond, the end diamond, you see this end diamond is all box at both ends and both planes. So if we have L7, M6, U6, etc., and in this plane, we add 100. So we get U100, M100, M100, L100 for the back truss. The two truss planes are separated by 100 numbers series, if you like, that series and this series. And typically these are called, there are hangers and there are posts. See, these are posts. These are a post based from the bottom holding up the bridge, the intermediate deck, road deck. Whereas this is a hanger taken from that connection, from that intersection down. These are called hangers, and these types of things which hold up without any this thing are called posts. So hangers at the intersection holding up there, and these are posts. Okay, so that is the nomenclature we have. Then if we look at the truss from the top, okay, the top plan, looking at the top of the truss, then we have what is called here a kicker. Typically, this is a K-shaped bracing, this is a kicker, and these elements, these two, are tubular members, specifically done so. I will explain to you. They're tubular members set very close to yield, and there's a lot of innovation in this project which I want to talk to you. I'll speak to you as it happens, what innovations we did. And you see here, it is flattened, but actually this is an inclined plane. From use, the end is actually inclined from here to here. And in that plane, we have a particular inclined truss called the portal bracing, which is extremely important to stabilize because all the instability accrues and goes to the end panel. And in that end panel, because it is inclined at the top, we have this special wind-based bracing and this very rigid requirement and it is critical for most truss type bridges, this end portal, if you want to call it, with this portal bracing in it, a particular portal bracing, very critical. And to make it rigid and prevent sway and ensure the load path down towards the bearings through the members all the way to the bearings at the ends, because the bearings will only be at the four corners. So at that point, we have to ensure the load path and rigidity at the end portal, and to ensure wind and destabilization of the truss. This is a very, very critical to have this portal bracing. It's a very particular design and very important to point out. Now, talking about these kickers, these are rigid eye sections, and here they're designed as moment taking so that they anti-sway. It's a very tall truss. We need anti-sway at the top. So these are full moment taking connections. Whereas these fellows, these are set, I'm telling you this, it's set close to yield. So Fy is yield, the tubular member is there. The cross section is there. We reduce the thinness of that tubular member such that it comes very close to yield, or when there is an earthquake, they will buckle, and in buckling, they will do work. They will store strain energy, they will do work, and they will dissipate the earthquake force. So, my friends, to tell you, this is one great innovation, first time in railways we did. And here we have intentionally created a structural fuse for an earthquake situation, and my truss will be safe even if I get my seismic zone 4 or whatever demand earthquake that may happen. It happens, my truss will not fall because all these K braces with their diagonals will first have to buckle and do work and dissipate the strain energy which may accumulate and agitate the truss. So here is a safety fuse, and the kicker therefore will have a pull at this point. So this joint here is designed very strong. Is this arrow being seen by everybody? Can you, Jyoti ma'am, can you see this pointer? Yeah.
Yes, we can.
So that point suffers an outward pull when buckling of these two members happen in an earthquake. So this is designed very tough, and this is simply removed. It is on a two bolt system here. It is simply removed and replaced. It is so cheap to replace. So it is an innovation of a structural fuse, probably for the first time and probably the only time in the history of Indian Railway. And I don't know about other cases, but it is a K brace we borrowed from a building where we have K braces and so on, and we can set them close to yield in the event of an earthquake. Otherwise, my kickers are strong because I've designed them as anti-sway. They are very good against sway of the truss because they're moment taking at the where they join the top cords. They are fully made rigid by brackets, etc. So now you see here at the bottom, these are there are two parallel lines. These two parallel lines are the main longitudinals, or the stringers we call them, which take the rail lines. Above them will be the rail lines are resting on these, the actual rail track. Similarly, so one on this side, one on that side, up track, down track, two rails for each. And in between them also you have bracing. And not only that, here too you have bracing. You have this bracing below the rail level. You have at the bottom, you have a wind bracing. This is the wind bracing, also at the bottom of the truss. And this is how the truss is stabilized at the bottom. And the railway two stringers are also fully stabilized in themselves. So this is a particular feature. And here you see at the road deck, the number of stringers are put, 1, 2, 3, 4, 5, 6, 7, so many. The roadway stringers are put, on which we are putting the precast plank and doing the road deck, cast in situ road deck is being done. So stringers are serving to break the length, 10.92 the length. They serve to break the length and allow for a better transverse distribution of the road live load, the vehicular load. So those stringers are put there. Now you see the top lateral bracing, as I told you, they are all of this type. The bottom lateral bracing, this one, the long crossing ones, these ones, the X's here, the long X's, they are of I sections, particularly of I sections, and not of flimsy star sections, because this is such a robust truss, and we needed to design not with star angle sections, which are very flimsy, and they, polar moment efficient inertia of star angles, two star angles back to back with a gap, are so bad in buckling behavior that we switched to a more robust I. This also probably for the first time in Indian Railways. Then the portal bracing, as I told you, is a very robust I section, and the kickers also very robust I sections. These portal bracings is this one, these, which I'm showing you, are of this. And this is what it looks like, a typical sketch of what it looks like. The two rail tracks, the bottom cords you see here with a line here, this is the bottom cord, this part, where my arrows. Then this is the truss going up. As you look at it from the face, it will incline. It will incline in the end, of course. There is an inclination in the truss. Then here you have at the road level pedestrian walkway, and also at rail level we have a gangway, which is not shown here but was added later, a bracket-oriented gangway for people to move or get evacuated in case of an emergency. At rail level also there's an externally bracketed gangway for people to walk, and in the middle for the walkway, and in the middle is what we call a gangway between the trains for people to go during inspection, etc., for the people to move, and that there is a gangway in the middle of this deck. Here you see the various stringers of the road deck with the haunching required there to get it integrated. The crash barriers and so on. The dimensions 10.92, clear distance. Then this is the top kicker, which you see here, which I showed you. And you see here all the various dimensions, etc., and the traction that is required, so on and so forth. All these very particular requirements of the railway with the moving dimension typically sketched in. It has to be shown to total scale in the figures and so on. Then a particular feature about designing a structure like this, railway have a particular, once you do the design, your analysis, this, that, load combinations, all that as per the bridge rules you design, you have to create what we call a stress sheet for each and every member. That stress sheet is like the law. The stress sheet, it governs everything, okay? It is like the most ultimate thing they have, and a very convenient way of seeing what are the axial forces, what is the member L0 to L1 and U1 to U2. We're talking about the bottom chord and the top chord. How much of the dynamic augmentation you have to take for those. Then what is the dead load they have, what is the rail live load, positive maximum, negative maximum when it is run, so on and so forth, what it weighs, and what are the actual loading in the longitudinal direction, railway footpath, total dead load plus live load, fatigue forces. Then what are the total basic forces, actual force, in plane moment, out of plane moment, from our analysis, etc. Then the wind forces, these are actual actions, right? In plane, out of plane moment, actual force, in plane moment, because we're doing 6 degrees of freedom analysis. So we get all that, okay? Now having that, the seismic forces, considering the seismic zone, this, that, as per the code, then we get those forces also. In the seismic forces, the actual in plane, out of plane, we get, right? Then the fatigue, F minimum, F maximum, the F minimum upon F maximum, the stress range, I mean, a reflection of the stress, the subjectivity to fatigue is a reflection of F max upon F min. And if that approaches unity, it is a very bad sign. Positive unity, it's a very bad sign. So you see, in a glance, you're able to make out the susceptibility towards fatigue, the kind of moments and forces that are there, and the top is the actions. Okay. Then the bottom, it is a contiguous stress sheet. It's a huge A1 type stress sheet you have to give for all the members, each and every, by running a live load, everything complete, you have to give this. Okay. Now you see the bottom. Here you have the area provided, the net area, and the member properties that we're talking about, I in plane, IY, X plane, out Y. Then the actual stresses, primary actual, along with secondary stresses, which allows us to have that 16 and 33% extra allowable stress, etc. Fatigue stress, then the combinations, then the allowable stress. Now, these are the actual stresses. Then the next bank, which you see here, in the lower table, is the allowable stresses, the actual stresses, then the allowable stresses. These allowable stresses are based upon, as I showed you in the design criteria, the bridge rules, etc. For that particular, we note those down. Then we have the actual to allowable stress, this column here, which is like your utilization ratio. This should never exceed 1. And mind you, here we're coming 0.9, 0.98, and this is an example. I've kept intentionally these. When you get something like it, it is alarmist. This member here, whichever it is, that is L1, L2 member, the bottom one is actually affixed. I've cut it in 2 parts and put one below the other. But if you see, it is bottom member L0, if you see on top left-hand side, L1, L2 line it is. L1, L2, it is a very tricky, it's 0.98. So we have to make it more stocky, more stiff, or increase its cross section and so on. Because now the outer dimensions are fixed. Now the only play you have is in thickness adjustments, right? Inward. The outside you cannot change. You cannot have, it has to be smooth. The outer envelope has to be smooth. It cannot change, right? And the gussets will come, the gusset plates will come on the top chord and bottom chord, rising up on each side of the top and bottom chord. And all the diagonal vertical members have to go into those gussets and be bolted onto the gusset. So that is why it is important to get the dimensioning right and the sizing right. So everything comes in the truss plane. Okay. And that is very important to remember when you do your preliminary design and sizing, right, of the members. So this is what a typical stress sheet looks like. Therefore, the section that we provide, what is provided and what is its shape. Okay, this automatically with the top plate, that one, it is 720 long by 22 thick, for example. So at a glance now, you have how susceptible is your member, then which is the gowning situation. You can go back and see whether it is fatigue gowning or it is a railway load gowning or it is wind or whatever. You can know and you can make the required changes in your design and the resistance side of your approach by knowing this. This is a wonderful thing railway have, and it is an amazing at a glance ready reckoner of where you are and what you are. And every time we update elements or increase thickness, this whole stress sheet changes, right? So another feature of a railway bridge is, you see, I've shown you, here is our inclined end, and this is the last vertical, okay? And here will be my bearing. And this is my end diamond, which I told you was a box section, and entire outside of my truss is a box section. Complete entire outside of my truss is also a box section, in addition to the end diamond, of course. What happens when you launch over the river, you do load shedding and you launch over the river, 100 meters, 123 meters free cantilever. It was probably one of the largest free cantilevering and the heaviest free cantilever probably done in railway at that time, or maybe even till today, I'm not sure. At a time, we were free cantilevering from one pier to the other pier before it touched down nearly 2,300 tons of steel weight. Without any concrete, of course, then we infill all that, the middle deck. So here again, you see the middle notes, you see the top notes, okay? You see two numbers written there. There's a nominal, and below that, if you see, there is a camber, adjusted length in camber. So every element, if you see, has two numbers written on it. One as a true design without any camber, and then with a camber length. So what is this camber? We shall discuss, okay? And why it is to be provided. As I told you, camber is very critical for something which exceeds say 30-40 meters, even for road bridges, but especially for railway bridges, because the railway, that live load is so heavy. The train loads and mineral loads and that the goods trains and all these things are so heavy that when they fly, the truss automatically deflects down, okay, under the live load. In any case, it will deflect under dead load. In any case, it will deflect. Even during launching, you can see three lines. The bottommost line, you see this line here, is during launching, and the steel only is 58 millimeter. You see here this value, 58 millimeter. This is to scale. This value is 58. With dead load only, it is, as you see at the top, 92.5. And in the center, as you see, the maximum deflection is 187. In the full condition, when it is in full service with the train, vehicle, it is full service condition, you can get 187 downward deflection at the center point of the truss. Okay. So you see that. And then that camber is adjusted, and this camber is adjusted. How do we adjust for this final condition? We have to create the camber by making certain members short and certain members slightly longer than the nominal length. Okay. That automatically hogs up the truss. It hogs up the bottom chord. The bottom chord is always kept to its true length. In our case, 123 meters. It is invariant. All the other members are adjusted and change their length to actually a length cut shorter than nominal as per my design, or cut longer than nominal as per my design, as per the annexure of the steel bridge rules. We are able to do by that what we used to earlier call the force Willett-Moore diagram type approach. We are able to get the force polygon, funicular polygon type approach. We are able to get the lengths and forces simultaneously in each of these members under the cambered situation. Okay, so there is a procedure in the code, in the bridge code, which very clearly tells you how to do this. The key thing is the bottom chord, whether it's a road or a rail, the bottom chord, that is, this bottom chord member, our box section member at the bottom chord, this whole length, is kept to its own length. All the other members may be designed to the camber length as per the force polygon approach. These days, we can do it in software, but traditionally they were done using that annexure approach. The point is that the real point is that we cater for the secondary stresses. In them old days, we never had supersonic computers and that. Everything was pin-jointed. These days, heavy deserts and all that, we are able to design with space beam elements, and instead of pin-jointed, all the joints are behaving actually rigid, more or less 100% rigid. So, of course, secondary moments will come up once you get fixity at the joints. And also the neutral axis of framing members are not at same heights. The forces traveling those members and the neutral axis are not at the same heights. So that creates secondary moments in each direction, each member orthogonal to in the direction of, etc., due to the framing. Torsion in one is bending in the other when they are 90 degrees to each other, two members, like a typical grilling. So you get those effects. To overcome and ameliorate those effects in the old days, they used to resort to a conservative approach, because we don't consider secondary stresses. We only design as a pin-jointed truss. We cannot have secondary stresses. Now that I've designed as that, it behoves me to do the camber also. And in addition, I'm doing the camber as a measure of extreme precaution. In the old days, you would have had to do it anyway because you didn't have your fancy computers. You would have had to do a camber correction, as we have shown here, with different lengths for the members to overcome the secondary stresses which will accrue due to the rigidity of the joints, which they could not cater for in their design. They were only able to do pin-jointed trusses earlier, right? And this is what the members in the into paper direction, all the transverse members, bottom lateral, top lateral, those kicker, etc., those are never cambered. There is no cambering into paper. Only cambering and cutting short or lengthening of elements happens in the face planes of the truss. Okay. Now the end makeup spans, the road deck is directly on top, which is what you see in bogeybill. Okay. The road deck is directly on top and the rail goes in this. Okay. It's a slightly different arrangement. I won't talk about it in this particular case, but just to show you what it looks like, it looks something like this. Okay. There is no further height of truss. I don't need it. The span is short. I need it to get my Z. You see the restoring couple T and C, right? Tension and compression in two opposite directions. Bending is maximum in the center of the truss. I need a double height truss. I mean, I needed that 18.75 in my 123 meter truss because of the span length. And it goes up, moment goes up L squared terms, right? So between 64 and 120, there's a huge difference in length. And because of that huge difference in length, my 123 meter trusses required that 18.75 meter height. And therefore, it's a two-level truss in the 123 meter, the road deck in the middle. And one further to get my Z, to get the Z, I need the Z to compensate the bending and moment which will happen in my service condition. In the shorter span, I don't need to get that much Z. What I have here is more or less sufficient. Now, the bearing layout is very, very important to understand. You see these bearings. So what you have here is a fixed end and a free end. Okay, there's a fixed end in a truss and a free end in a truss. Okay, the circular, what you see, A, and EE, at the fixed end, we have a fixed end bearing. Okay, and here we have this the center line of the bearings. By a very clever arrangement, we extended this bottom chord to get this separated longitudinal bearing here. So these only take vertical reaction. The longitudinal action is taken on this bearing and the transverse action is taken on this bearing. These D and D are the jacking points. So when the truss is agitated in this direction, if my bearing fails, the longitudinal effect, only the vertical is taken here. The horizontal, I have to separate both longitudinally and transversely. So I have to provide bearings B and C because of that 25% exceedance rule, where if the horizontal forces exceed more than 25% of the longitudinal vertical reaction, vertical reaction in the vertical direction. If my horizontal forces exceed by more than, I have to separate the bearings for horizontal action and for in both the directions. Okay, so there I get B and E, and this only takes vertical. Okay, and here you see between B and D are the jacking points in which I will lift the truss, so I can replace my bearings in the future by lifting the truss at jacking points D, which are on the end cross girders, which are I section, very robust I section cross girders. Again, so it is easily weldable to a box. It's easy to rivet a box or weld a box with an I section. Box to box welding or box to box riveted connection is a hell of a nightmare. Okay, so that's why you always try and keep your end cross girders as I sections, please. Try and avoid, or a double-headed I or whatever, but try and keep I sections at the end and not box sections for the end cross girders. So this is the situation I wanted to tell you, how the clever bearing arrangement has been made so that in the longitudinal direction, this will take the seismic action and fail, and this will take the longitudinal seismic action and fail because they're designed for seismic as well as horizontal or longitudinal in each case. Once both these fail, once both those fail, it fails, all those bearings fail. They are designed for 1 times the seismic force in the longitudinal and transverse direction, as I showed you for the bearings. Now the bearings fail. My truss has done its job. The fuses have gone. My bearings have failed. My second tier, my bearings have failed. First, my top fuses have blown, as it were, and they have done their work. Then, even then, my seismic case design for my bearings is there, my pot VTFE. Then my pot VTFE bearing also fails. I have a second fallback, another phenomenal incorporation in this particular project, 2 times the value of seismic. You see the lower table, 1080, 2 times 540, and 560 is 2 times 280. In the longitudinal and transverse bridge, the seismic restrainer specially designed for this bridge and used a very unique concept, done and innovated for this bridge, are 2 times the seismic force at failure of the bearing. So my truss not only has a fuse, then I have the bearing which will take normal seismic, then 2 times the seismic will be taken by my seismic restrainers, and my truss should not nominally fall even under a very severe, very, very demanding earthquake. This is the robustness of this truss. This is what we innovated and put into this truss. In addition, you see between, I told you, we built up the pedestal. This was you see this small area here was the original pedestal for the 2 bearings considering 1 railway line, and no road, no nothing. Then we built up the whole pedestals of, say, different thickness marks and different heights. We built up the pedestal like sort of like beam zones. We thickened all this. We built up that measly pedestal by putting hilty downward U-shaped anchors at, with a good spacing, properly designed, everything and all. We put all this, which you see hash shaded here, is a built up elevation of the pedestal and augmentation of the pedestal size. And you see here that between pedestal of that span and built up pedestal of this span is trapped a downstand in steel of the longitudinal action seismic arrestor, and here the transverse seismic arrestor, this being designed for 2 times the seismic failure force of the bearing. So this is the innovation which we used, and these are designed then to take that 2 times the seismic force. The pedestals are now to resist 2 times the seismic force because the original structure as given to us was completely deficient only in this one issue. It was robust in the substructure, foundations, everything perfect for all this increased huge amount of demand load, but it was incapable of handling the earthquake, especially the 0.12 G from the site-specific study. So we built in this double safety measure into this particular bridge. And you see here how from the top, the steel section, we take a downstand in the longitudinal direction and that similar transverse sustainer in the lateral direction. And they are located in the previous, this one, the transverse, and this one, the longitudinal. And you see inside here all the various stiffeners that are required to stiffen it to take that 2 times P force, crushing force between both the resisting pedestals, this downstand. So this is a very clever innovation. I don't think it exists on any other railway bridge in this manner. And all these members are designed for 2 times seismic. All the riveting, everything is all designed for 2 times seismic force. An extremely robust design. I'm showing an example of this downstand and how the elastomeric pad is inserted there to reduce the sudden impact during the earthquake. Even for that, we have put in an elastomeric pad, which can breathe during normal movement, etc., of the truss, for normal movement of the truss temperature, etc. All movement is possible, right, in that gap. So here you see the stiffeners that we've had to put. I'm showing you a plan and how these stiffeners are put. Then a problem happened about how they should be closed, how those should be welded and where to close it, etc. There were so many stories to be told in this, and the construction methodology, we gave 2 options. How these stiffeners, how they should be welded, fillet welded, butt welded, what, and how the top plate should be closed, because once everything is closed, then how do you close the top plate of this, and so on. So all that we had to give the schemes and think in great detail about that. Here you see in dots, the dots that you see in this figure, all these dots are the U-shape, like this U-shape, okay, deeply embedded, epoxy grouted. Here we have the epoxy grouted part, and here you have the projecting part into the built-up pedestal, as I told you, this built-up pedestal, pink shaded pedestal. And the little dots you see here are the arrangement, and you see here these arrangements. You see here are the pins, and here also you see in here are the U-shaped pins, like this U-shaped pin, which are inserted and systematically organized to augment the pedestal's ability to take 2 times P and send those forces down into the piers. So this is the pier cap and then into the piers. Now, this is a supreme innovation, I would say, in this project. I hadn't seen it anywhere else, and this is how we went about doing it. The failure modes, as you know, there are 3 failure modes that happen for that typical member. How much should be this depth of burial, which we have to drill into the existing concrete pier cap? How much should be the depth of burial of that U-shaped bar? There are 3 failure modes. You see, the failure mode of a bar, when it's epoxy put in, it can either fail by the bending of steel, because it will fail without this coming out. Let's start at the other end. The easiest is it will completely pop out of concrete. It will pull out of concrete directly because of insufficient bond length. Or it will fail because the epoxy is useless and the epoxy doesn't hold, it simply pulls out. Or it will fail by bending and failing because it is so rigidly held inside the drilled hole that it can only fail in lateral bending of the U-shaped bar or the anchor. And this is the most preferred steel failure mode, is what we designed for, because after all, we're depending on 2P. At 2P, we want everything to go in yielding, right? We want to have the full reserve of yielding in my steel bar so that my truss does not fail. Even that we are getting the ductility of steel. I am telling you, this is the way we have further enhanced the design. And we use this Hilti Headkit 500 to drill and blow into the hole. We drill a hole, we put that and so on. And the whole depth was sometimes up to 1.6 meters into the very deep pier caps. And this is the resin pack, the drill gun, etc., to shoot the epoxy in. And you see the failure mode. Now, this in green, these are the green failure modes, okay? Blue is what I want, okay? Here is my depth of burial. And you can see 1 meter, and then a factor of safety, etc., and all we have to add to it. So you can see 1181 centimeters, that is 1.18 meters for getting this failure mode. And for getting concrete cone of failure type, cone of failure of the concrete, we can get at, if you go up to 250 meters depth of burial, anchorage is 250 of my anchor, it will fail in simply by concrete failing, and I will never be able to reach the value of yielding that I require to ensure that 2P is available to me by the failure of all these, and everything goes in gradual failure, right? Successively go in gradual failure. So this is the level of innovation that is there in this truss, and it is, I think, quite unique. You can see the Hilti is being installed, blow, dry, etc. They've got a particular quality control procedure. Then pull-out tests are done. We see with the max pull, the pull-out test is done and calibrated, and actual pull-out tests are done to ensure I get my yielding of the yielding failure mode of the steel rebar, and not by failure of concrete. Now, how about erection? Initially, we do trussels on the anchor span. In the shore side, we build up all these foundations, we put these trussels. They are called Christchurch cribs. They are very easily available with the railway contractors. They build up this, then they give proper bracings and all that, well braced and all. And then this 123-meter span, on that, from the road, we will erect and put up, I mean, we have access, there is dry area. in the dry area. We will, not a wet span, a dry span. We will erect this and make this a truss on top, and we will do it with a, and then put a crane on top. Okay, I will show you that. I will show you how that is done. So we triangulate and complete the first truss. I will show you in photographs. You will understand that better. And I'll show you the erection sequence in photographs, which you will better understand. So now suppose we have finished the truss. We have finished this truss. Then we put a crane on top. This is called the main erection crane. We put a crane on top of the already built truss. We take away all those stagings. Here we have a feeding system. We take away the stagings from below. And now on this field is suspended, I mount on this spanning between two piers. I mount my erection crane, and it goes on rails on the top end girders, the top booms, top cords. They will go, the railway track, temporary railway track is laid, and on that railway track, this main erection crane, which you see on top, moves at the top to then start triangulating and building up the forward truss to the next 123 meter from one end to the other, and it goes. Okay. For doing that, in between both these, I tie them with a so-called link element, and we tie both these because remember, these are inclined members in the end. The end is an inclined element. You see, this is an inclined one. So between the two inclined, I put in a T-shaped filler element, which have turnbuckles to adjust the tension and lower and increase the height. And here we have hangers, what we call hanger. Here we hold up the bottom cord by a hanger from the previously erected element. And so on, we go ahead by holding up with hangers, putting in the bottom cord, and then finishing up the triangulation. The feeding is done in the lower level. There is no road deck. Load shedding is done, and we try and push this from one end to the other end with duly load shed. We remove a number of the critical members which are not required, and the lightest possible span is then tried to be erected here. Of course, here we will put in everything because this is a ballasting span, which because of the T arrangement here provides a hold back. And as this goes on free cantilevering, this crane position and counterweight and cantilage that we have will be moved further and further back. This is a follow-up crane. This is the main erection crane doing the erection of the forward span. Okay, this is the already built span. So this is the philosophy that we do. Then when this span touches down on the other side and this truss is closed on the bottom cord, this main erection span, now this is completed, right? And this fellow is already waiting there. Then he can come forward, and all these load shed elements you see, which we'll have in this truss, which have not been filled, this follower crane will take from the dip lorry which will transport on the rail, temporary rail at the lowest level. This crane will pick up from there and start filling in and doing up all these intermediate, all this business. It will start slowly filling up. Okay. So that is how the load shedding is done for forward cantilevering. But once it is finished and touched down on the other side, the follower crane will then come in after it has served its cantilage function. It then comes in here and starts doing up. The follower crane does the filling up work of the load shedded members. So I won't get into much detail, but in a nutshell, I've told you how it is done. Okay. What is the problem you get? If you're an engineer and the contractor suddenly changes the concept of erection, or you as an engineer have not pre-thought the way this will be erected, or you as an engineer come into some situations where the contractor does not get certain thickness of plates and then the whole thing changes and so on, then you must have a contingency approach. In this case, for the first time, because there's such deep webs, you see the web is 1.36 deep in the bottom cord. The web L0 to L1 node, L1 to L2 node, 7.5 meters and so on. It is multiples of 1.36, right? 1.36 meters, 7.5 meters. So if you consider squares, typically in compression, plates buckle in waves, anticlastic waves, sinusoidal waves. So this sinusoidal wave of buckling has a wavelength of A by B4. And in a 7.5 meter span, 1.36 times 4 almost happens. So this typical web panel here became susceptible to in-plane buckling in waves, in the form of waves, typical plate-based compression buckling, because of the depth. Okay. And now, though we have diaphragms to arrest and so much stiffening, inside we have diaphragms of the box. Of course, at each node, you have to have very strong diaphragms to arrest torsion and so on, and especially over the bearings. We have 3 lines of diaphragms over the bearings because of some accidental shifting over the bearings. We have 3 very robust lines of internal diaphragms inside the box so that the load path to the bearing is ensured. inside the box down into the bearings. You see, from inside the box into the bearings. Now, the point I want to tell you is that these were originally 22, because in service, the bending demand and the buckling of the web will happen at the middle because of sagging, right? So the maximum bending moment demand, etc., plate thickness demand, etc., happens in the middle of the truss at 133/2. Whereas when we are free cantling and erecting, in a situation like this, as we go on increasing the length, before I touch this one, this will sag. This will sag downwards. When it sags downwards, the top will go into tension, the bottom will come into additive compression, and at this location here, against this buffer block, which I've introduced between these two bottom cords, a buffer block of solid steel, between that buffer block will come a huge amount of compression. And this, which has been designed for tension in service condition, under maximum compression, it's a complete reversible of forces. That which is designed in tension is actually under compression during erection. Complete stress reversal. So the plate thicknesses then become very important. We thought we had it right, and we thought everything was good until we had to realize that it is not possible. So two things were done. The grade was changed from E350T to Fe590E, which is a very high strength steel, and the thicknesses was changed from 22, which is a service condition demand, to 32 in L0 to L1. And between L1 to L0 to L2 and L2 to L3, those nodes, that bottom chord member was changed from 22 to 25 thick. As you see here, you see this 32 and you see this 25 to resist the buckling, okay, to prevent buckling in the form of waves, what we call plate buckling phenomena from happening due to the compression being involved by the launching operation. At the maximum cantilever condition, it is the worst. Okay, just before you touch down on the other pier in the free cantilevering condition. Similarly, now that I've increased this, I need to handle Z, right? Z is I by Y. So when you do in compression side, you have to compensate on tension side, which is the extreme top. And there also, I did need to change the thickness of the web, the flange, the TB1 and TB2 plates, as you see here, the web or the flanges. I didn't have to change the thickness, but I had to change the grade to handle the additional stresses that were coming from the increased compression at the bottom, the compensatory Z requirement. I had to increase the top plates also in this case to compensate. So, only in terms of the grade of steel, I did not have to change the thicknesses in the top. Bottom, I had to because it was buckling prone, of course, in compression. Now, some photographs. These are typically the holes which are, very systematically drilled and so on and so forth. I won't get into the fabrication stage today, but these are typical stiffeners. These are typical eye sections. They are lying at side. Here you see the hat type section with a projection of the end diagonal or so. And the various types of members are put at site. And here you see on staging, the shore span, the ballasting span being erected on this shore base staging. At the back, you see 123-meter each pier going out over the horizon. All those being the piers which are already erected, and on which, of course, the tops of which the Hilti work and the pedestal augmentation and the seismic restrainer innovation was all done. For all those piers, it was done. So typically, you can see what I mean by a gusset. You can see the size of the man, and twice his height is the size of the gusset. So obviously, pin joint, it is a ridiculous philosophy. It is definitely fully rigid. And here you see how a gusset plate is being put onto the bottom cord or so. You see, these are drift pins, and they have drifts and they have pins. They shoot them through these. Sometimes they ovulate the holes. The holes get ovaled. And because of that, hot riveting is still preferred by the railways, even in spite of HSS reports. A rivet is heated hot in a tandoor, and that is hammered from both sides with a dolly to give a shape. A red hot, in a tandoor, it is put, and the workmen hammer it up, and they make the rivet. Before that, to hold the things roughly in position and place most of the holes at some critical points, they will shoot the drift pins in. They are just drift pins, and they actually sometimes change the shape of the hole. And because of that, a hot rivet goes and fills up all that gap, that untoward gap that happens. It fills it up, and it makes the hole completely filled up because it is put in hot, right? And closed and hammered. So this is a typical what I want to show you. Here you can see the rivet gun, hammer, or whatever you call it, riveter gun waiting there, the riveting hammer waiting there. The triangulation being started here, you see the mid-level, this is the road level, okay? And here you see the bottom chord is laid out with its gussets. Then the triangulation, the vertical, this, that of the shore-based span is starting with this erection crane here on the right. We typically pick up full sections and put them up, easier to do, assemble on ground. That, mind you, before this, the trial assembly has already been done and certified by the RDSO. The trial assembly of the elements has already been done and it is certified by the RDSO, and only then we are able to bring it to site and do the site-based erection. What you see here below are camber jacks to impart the camber, by pushing upwards, the camber jacks to control this thing. When the size of these elements are, of course, all with camber lengths have been now put in. Here you see the road level cross member. Here you see the end girder cross member. Here you see the pier, etc. All that pier and all that. And you see the crane doing the erection work and filling up until this end part here you see. And you can see here the way it is done on staging, and we complete this up to there. Then what happens, we put in this temporary link element in blue, you can see here. At the end of the truss, we put in this temporary top element. Out here, we have moment taking, we have a little twisting ability, freedom to move a little bit here. And here it is resting on this part. We then go ahead, putting the next member in the forward member, we see here. And closing is done on the last panel. The bottom chord goes across. This is still in the dry spans. The bottom chord goes across, and then this end member is pulled, and the truss is then closed. Okay, this is a very important action, closing of the truss, right? And here we were lucky, we could still do it on staging for a couple of spans. And then you see here the shore truss span erected completely. And you can see the various levels people are working, etc. Here you can see, you can go through the hollow, you can walk through the box required for doing the riveting, etc. from inside the box. Similarly, the hollow top chord member. Here you see two holes at the end through which people can go and do the riveting action inside the box. There are oval holes which will then be covered by plates. You see, so that you can work inside the box. The box is so big and deep that you need access in the main members to work inside the box, which is given in the, I'll show you. Here you see the road stringers, typical road stringers. Here you see the most important end portal here in this cross plane, in this inclined plane. In this inclined plane, you see that main post like a king post. You see this end, this very, very important because it should never sway. There should be no sway that happens here. Otherwise, there will be a lot of problems. And the load path of all forces ensured through this and goes straight into the bearing. The entire load path comes here and goes into the bearing. So this is a very, very important item and requirement in such a kind of a truss, in this inclined truss, in this inclined zone that you have that end portal, a very important feature. So you can see here the work being done. Then you can see we have brought to site here the table for the erection crane, which will go to the top of this truss. Okay. So you see the size of a human being here, and you see at what height we are operating, and it gives you scale, what scale we are talking about, the size of the truss. The turntable of the, it can rotate. This top main erection crane works on a turntable which rotates, and here it is assembled, tried at ground, disassembled after it is load tested, etc., disassembled, and then erected with a mother crane, a crane lifting a crane to the top, and it is being assembled. Here you can see the temporary link element in blue color, which is filling that gap between the inclined face of this truss and the inclined face of that truss. And you can see how it rests here. And it's a very critical element. As you can see again in blue, the link element being done. You can see how the crane is lifted, its boom is lifted, etc. The whole crane is assembled at top. And here you can see the moment like a mechano, the moment ability out here. You can see here also the hole for the next member, and you can see it will go. This is the next truss. Here is one pier. And on that pier is this truss which goes leftwards, and here this truss which goes rightwards, and the erection of that has just started. And this is the temporary link element. Since it can be done on staging, this link element was just being assembled. We insisted on those bearings below here at this point during temporary bearings during erection, before the main bearings are put, these knuckle bearings. And it was good we did that because, and good we were vigilant, the cracks were developed. If we had not been involved with the supervision and vigilant, And Mr. Srinivasan, our site in charge, excellent engineer, he used to go everywhere in the truss, everything he used to see. Brilliant man. If he had not noticed and sent me this photograph and said, sir, I see something is wrong, I said, stop the erection completely. When you see something like this, if I have 2,300 tons over the Ganges and you have a crack like this, for whatever reason, fabrication, poor material, it will just fail. This bearing will fail and my truss will collapse. The truss is after all sliding on this knuckle bearing during launching to a sliding situation. It will simply fail at this point and my whole truss will come down. So this is one issue that happened. Being vigilant as supervision consultants, we stopped the erection and we could prevent that. Between the two bottom cords, this is the concrete end plates and this is a buffer block. We insisted that it should be held up and tight because we didn't want it to slip. And they wanted to keep it in free air like this. The erection consultant, we told them to put it on a stand. Like when you have a jack, you have a packing below. In case the jack fails, you have to come down on packing. Similarly, we insisted on this. There was a lot of resistance, but finally we got what we wanted. You hold it up at the top with your wire, I don't mind. But at the bottom, I want a positive so it can't slip too far down. Notice the curve because when we're launching, we launch upwards. The whole forward launch is that at a forward inclination. It goes on losing the forward deflection, comes down, 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 till finally I reach the other side with the maximum free cantilever weight. I touch down on my bearings. My endeavor is to touch down on my bearings on the other side, on my temporary bearings on the other side. So that's why this is shaped like this, because we launch at a certain degree upwards. We don't launch horizontal because of the sagging moment upwards. Here's a clear view. You see the temporary link elements tying this truss, which is acting as ballast for this truss. Here that has already happened, okay? And here you see this temporary link element done. And here you see the erection already happened. We are about to touch down and close on the bottom cord member. Here you see closing on the bottom cord member, in this case, not the vertical, closing on the bottom cord member, some jugaad system here in the water. This is the first water span in the water. And you can see how we have done load shedding. Sometimes we're requiring some temporary elements, some members. We did this in the first case. We don't need it later on, but we just wanted to make sure nothing would happen in the first wet span. So we put these members to see if they are undergoing any stress or forces. They were not required as per design. Later, we did not need them. And as you can see here, a lot of these members, the whole road deck, the complete road deck of maybe 1,200 tons of concrete deck is not there during the free cantilever launch. Only the bare steel. So now once I complete my truss, the camber, this upward camber that I should get at the bottom cord in the center, it should have hogged up by that 57 millimeter. When I've completed my erection at the center, I should have a hog up of 57 millimeters as a camber. So that all has gone well. Okay, that the erection has all gone well with my steel weight only. So this is the situation of free cantilevering. On one side, it was water everywhere and we had to make a temporary bund. And over that, you can see we had to bring from the side and dry feed. And feeding happens not at this level. Feeding happens. You see the dip lorry here. This is the dip lorry. We feed all our elements onto this. The fellow goes zoom ahead with a winch crane all the way to the front. And from this level, because the road deck has no member there and one truss, two trusses behind, we stop the road deck cross frame members and cross members. And from the dip lorry, which is here, this fellow picks up from the central feed, from the temporary, dip lorry, the dip lorry being on temporary rails below, it picks up the elements and then helps in the triangulation of this forward piece of the truss. Okay, you can see that there are these hangers here. You can see these temporary hangers that are given, which are nothing but wire hangers holding up the truss. A clear view, you see this, it can rotate partly at these points, at these moments. And here you see the bracket on which all this is fixed. Everything has to be meticulously designed, and you see the cross members, cross trusses to take and hold this rigid, because this is what is transferring the moment. It becomes a two-span continuous structure. So the moment that is happening in the hogging, when it is hogging downwards in the front side, gives a upward moment in the back span, which has to be counterbalanced as the two-span continuous, which is changing all the time, of course, as you increase the length of the forward truss in the cantilevering. So the ballast and the cartilage are used in the backspan when required. And these are the very important features of pre-cantilevering arrangement, which you can see happening now. Okay. Here you see the follow crane. We have touched on the other side. The follow crane has already come and started to do its work of filling up in this truss all the left out load shedded members during the erection of this truss. Now that we have touched on that side, we are on temporary bearings, etc. We are robust. Okay, then immediately after those members are taken away and this fellow has done filling up of all the steel members which come on this dip lorry, which come at this level on a dip lorry, it picks up and fills up all the road deck and whatever load shed members, etc. It has finished its work. We remove this temporary link. So that blue temporary link is now removed. It is over. This work is over, right? And we go on with the free cantilevering arrangement ahead. If necessary, we can always put another crane, follow a crane on top and do this. A crane like this costs in lakhs. Can you imagine the innovation of working over the Ganges? We erected 36 spans without any accident, no loss of life over the Ganges. So full erection supervision done by my firm Consumer. Here you see the temporary rails and how that dip lorry at the end feed, it is rear feeding from the shore side. We fill up all the stuff that is required, this member or that member in the forward part of the truss. It goes by a winch, operated by a winch. It goes pulled by a winch, this dip lorry. It goes by this winch. It is pulled ahead to where required and the crane picks up. The lorry is there. It picks up and triangulates the front of the truss. You can see here a wire which is holding up a temporary hanger, what we call a hanger wire in steel with a turnbuckle arrangement. You see that slightly upward kink because I want to arrive there, just above my bearing. So you see it is slightly upward and the buffer block at the back, of course, has that little curvature I told you about, curves part. And here you see we're slightly nose upwards. You see we're slightly biased upwards so that when the full weight at maximum cantilever comes, I touch down. You can clearly see the hanger elements used to pull up this bottom cord. And by the turnbuckle arrangement here, we line up all the holes of the rivets by clever use of these hanger elements. And we line up all that and then we put in our bolts and drifts and then we do all our riveting. Okay. So this is how it works. You see that on the turnbuckle at the top. He picks up from the dip lorry at this level. The road deck is yet to be done. Okay. Other views, all different views. You can see how from the dip lorry here, that fellow has been picked up by the top thing. And this is the tube I told you, whose diameter has been specifically chosen to set it, thickness has been specifically chosen, diameter and thickness, to set it close to yield. You can see how they are joined by just a very flimsy in-plane joint here, just sufficient. You can see this joint here. This is also a characteristic design, and they go and join these kickers, in between that K base and the kickers at this point. This point is very robustly designed. You see where the two tubes come and join, very robustly designed. And these tubes are the fuses which I spoke to you about, set close to yield. So when the earthquake comes, they will yield and keep yielding and do their work by being close to plastic, buckling and that. And as they buckle and as they go plastic, they will start to buckle and or yield and continue to do so and dissipate the earthquake force. Sometimes we need jugaad like this. In case it is not coming at level, we need to put some jack on a floating arrangement and lift it, because it's not a joke cantilevering 123 meters from pier to pier. This is from here to here is 123 meters. You can run more than 100 kilometer race inside each truss. You see that jacks and all that. Sometimes we need here also, so that it comes onto that bearing. Here you can see a clear view of the heightened and fully integrated built-up pedestal. You see what I was telling you about. The fully built-up and integrated pedestal on that side and on this side. This little white arrow where I've shown you. And this is the simple views. You can see the tubes at the top. You can see the road deck level cross girder coming in here, road cross girder, rail cross girder, how they are framed. And you can see these cutouts in each member for man to go in to do the riveting inside. Afterwards, these are closed with an FRP plate or a steel plate. It is closed and sealed for preventing water from going in. You can see the man gone inside to do the riveting of all these. The pins, you can see projected pins and drifts to get the alignments right. The joints are so complex, getting everything aligned. We need to pull this fellow up with a hanger, pull him up so that he comes in plane with this fellow and all that. Then the gussets here will be put. so on. So all these access, inward access by these specially designed oval cutouts. Yeah. Here a close-up of the turn. Here there are turnbuckles. By adjusting the turnbuckles with hand, you can pull up, you can adjust the tension to pull it up or push it down. Okay, and that is how we do the over the water. Just the size of the cutout, you can see if that is the size of man, what is the size of the cutout in those bottom chord elements. Then connection of the top bracing, I told you these tubes, how they are connected. You see, this is the diagonals at the top, going down from the top chord. Here is my kicker. You see, this is the kicker, very robust, moment taking. You see the bracket also. It's a fully moment taking connection. When you hold the flanges robustly, then you take moment through the flanges and also through the webs if they are very well fully connected. So it's a moment taking connection, of course, because of sway in a portal, right? So that is a sway moment taking connection. And here you see that thin plate and the fact that this fellow will buckle and then go plastic and continue to do work, these fellows. And this is the typical arrangement that we have. And here will be the other members. See, you can see that coming to this one, this coming to this one, here and joint here. There and joining on this kicker, and we put special extra strengthening at the kicker location, at the center of the kicker. You see the various band going on the deep lorry, then the rail stringer, the road cross girders coming in, the road stringers or road cross girder, road cross stringers coming in. A typical joint of members, how complex it is, and drifts are, all the riveting is yet to be done, and so on, right? And typical rivets, how they are shaped by that heated rivet. Maybe it is very cruel, but it ensures that the hole, because of the drift bolts and pins that they use, pins and bolts, drift bolts, the perfect hole is made over-shaped, or it is, then under-reamed or over-reamed. And then that has to be completely filled up only by this red hot, and hammered into place the rivet. Again, you see a typical joint. At the bottom, the eye girders, the eye wind bracing at the bottom, which would have been star angles, but are very robust wind. You see how one member goes through and the other member comes onto the gusset. Okay, one member goes through, the other member is cut here and is held on these two gussets. Okay, this is also what you have to see. Always in an X like this, one member you should take through, the other member you should rivet and do up the joint so that the effective length of both the members are then controlled. The issue is, of course, to break the effective length. Okay, and buckling. So some snaps showing you what it is to fill a truss, and the awe with which these people go to this structure is something. It makes me very proud that you can't see the other end. You just cannot see, and clearest of day also you can never see the other end. It is so. This is what it looks like finished. Okay, these are snaps of in use just before, prior to commissioning, the approach road going on here. You can see the road deck and entering the truss. This is the approach viaduct. You can see, and you can see some photographs here of the truss just before commissioning, some finishing works, etc. Few days. The road deck, concreted road deck, you can see here. Some finishing just before the work is completed in all respects. Just prior to that, this photo was taken few months before opening to traffic. And then you see here the length, the actually completed structure, and people going there to just look at it in awe. You see the curves over the horizon. Even whatever you do, you can't see the other end. It is curving over the horizon. A book. This project inspired the then CEO Madhuresh Kumar and Mr. L.M. Jha to then get together and write this book on the journey of Patna Rail Road Bridge. And it was inaugurated by the Prime Minister. At one point, two of my projects were in the Prime Minister's monitoring list of 50 projects, Munger as well as Patna Rail Road Bridge. I want to tell you that a book has been written so unique is this bridge, and so deserving. I think that what we did is documented. You can buy this book, from it is in what you call, just come out in Flipkart. You can buy this on Flipkart, and it is available on Flipkart. Okay, so another project in which myself and our panel member, Mr. V.N. Hegde, were deeply associated him on the construction side, me on the design side, is probably India's most significant stride in bridge engineering. The signature bridge in Delhi. It is a cable stayed bridge. Everything you see here is in steel. The pylon is broad definition with the Namaste beckoning you to the east of Delhi, which needed to be developed. The pylon is a symbolism of modern India reaching out and an aspiration of youth to be modern and to progress and demonstrate to the world that we need modernity, and it's a reflection of that. The deck is a complete steel composite deck. So at some other time, maybe I'll talk to you about its design and the steel composite deck. There's so many innovations here too. In not only the deck, the foundations, the deck, the superstructure, problems overcome during construction. There is so much to discuss, and I will save that for another day. Thank you very much. I finished this part of my talk. Thank you all.
Thank you, Dr. Harshavardhan. Really very well explained all the concepts as well as so many innovations related to the analysis, design, and even the construction aspect of this landmark bridge. It was really an interesting, I'll say very beautiful presentation also with a very, very exhaustive information. You are just going to be bombarded with.
One
Yes.
second. You must have a lot of questions and so on.
Yeah,
so
that's what there are about 22 to 23 questions.
As you like. Whatever you wish, I'm available to answer it.
Yeah, we'll just see because it's already now 7. We'll take few questions which I'll find more relevant. Let's take some important questions from those. So let's start with the first thing that you told about that while modeling, you said that the joints were modeled as rigid connections. So whether they were really rigid connections or they were with the rotational springs.
Fully rigid.
Only rigid.
Because you can see what if some of the joints are 2 times the height of a man, and how hundreds and hundreds of rivets in some cases. Where is and so much framing, robust framing. Members are also so robust. It's going to behave only rigid. It is no partial fixity at all. It is completely rigid.
Right. Then next, immediately the next question asked by the same Likhan Biswas, he has asked, in FE analysis of buffer plates, what was the boundary condition and how the loads are applied?
No, you see why FE analysis was taken, the brick elements were used, and we were interested to know the stresses. The stresses is what we're talking about. It's not the shape. The shape is governed by the expected geometry when we come down on the other end, that curvature in the shape. But what is important is at maximum cantilever, the compression cord from one side, it's trapped between the existing already launched and the being launched at the bottom cord is the buffer blockade plate, right? Now, the steel buffer block, it is the plate, if you want to call it, in steel, that the stresses are very high, during erection. So that size is of a certain size. So whether that thickness or we have to increase the thickness, that with brick elements we have to model in FE and find out the stresses are not being exceeded, and whether the grade of that steel, etc., are sufficient to handle. That is why we did the FE analysis. Okay.
The next
boundary
question,
conditions and all, it's not for this event.
We cannot go into that detail, right? Okay, next question was been asked by Dr. S.K. Dhawan. It is a general question. What is the life of the PTFE bearings or even the life of the bridge, and how do you monitor its structural health?
Okay, now the structural health monitoring is not done on this bridge now because the railway have a very robust, Ravindra is here, he can tell us, the railway have an amazingly robust method of inspection. And in fact, what is not told is there are inspection gallery and there's a small area at the end of each span on which the inspection wagon, they have a small inspection trolley, which can be pulled aside and parked, and the train can pass. So there is also that facility. This bridge is under continuous inspection by the railway schedule. So there is actually no need for structural health.
The structural health, right. Okay.
But the life, ma'am, it's a 100-year design life at the very least. That is for sure. And pot PTFE bearing we should expect between 20 to 25 years what we expect, but that is as per the bearing manufacturer, Majida.
Okay. Next question is related with the impact factor. Mr. V.L. Deshpande has just written this. This is a unique structure unlike normal structures encountered in the rail or road bridges. Also very large span. So is it adequate to consider different impact factors given in the respective codes separately for each load, or is there a common impact factor that has been used?
Right. In fact, the significance, impact factor, two things, ma'am. One is impact factor. Mr. Deshpande, thank you for that question. I think all in the audience must know that he's one of the most foremost designers in this country. And the question is very, very pertinent, because what is impact? The impact from the road has very little significance when you compare to the impact of a train. It is simply swamp. So I would argue that even if we ignore the impact from the road deck on the total truss, it has very little to contribute. The other issue is fatigue. If we ignore impact from the rail, we are infringing on the fatigue range, the fatigue stress range. So it is very, very important to consider, even from fatigue point of view, the impact from the train. That is, it swamps everything. Okay. So that is why we have taken impact for the road. It would have made no difference. A common impact factor we cannot give, because the rail behavior, that lurching forces, that so on and so forth, the way the train behaves, its interaction with the rail is totally different from the road surface. Wheel-rail interaction is totally different from the tire road surface interaction. So that is one of the reasons we have kept the impact separate. It would have made no difference if we had designed without impact the road deck.
Okay. Okay, next question by again Likhan Biswas. When you use the bracing system as a K-type, so which bracing system is better, K-type or X-type? Because for K-type bracing, effective length will be 2 times. So I think for the top bracing, he has asked this.
Yes, so that helps me. I want it to go in buckling. I want it to then start in the buckled state, so that I can dissipate strain energy and save my truss. You answered the question yourself, Likhan. Thanks for that question.
Right. So your structural fuse concept that works better in K-type. That is what you want to say. Yeah. Okay. We'll skip a few questions. Those are very general. Okay. Why were rivets used instead of the SHFG bolts?
Now, HSFG bolts, this was part of the design requirement. We requested that. It was not allowed. And in fact, Railway are very strict about welding across the direction of stress. So in a direction, particular the bottom chord or top chord, welding is more or less prohibited. Okay, it is not number one. Number two, just ask the question again, ma'am. What is, sorry, I missed that once more.
Just a minute, I just skipped that question. Why were rivets used instead of HSFG?
And HSFG bolts were not used because at that time the code for HSFG bolts also had yet to come out. Railway have a code now, and the design, at the time they did not want. Madhresh Kumar was very clear that, and chief engineer then were very clear that only rivets. There is no question, only rivets. We don't trust the bolts, etc.
So generally for many railway bridges, you are having the riveted connection.
Largely there is a reticence to use HSFG bolts in railways because the size of those holes with the drift bolts, when we hammer in the drift bolts and pins, that exact circularity of the holes get oval shaped and this, that, and it get distorted. And there is plasticity when that hammering at the end of those ones. So a hot rivet which goes through and through the plates, the various plates, gusset plate, this plate, that plate, connecting all the various members and plates through and through at that location, through the gussets, gusset at front, gusset at back, trapping the members in between. That it should not, have some mismatch, or because of that underreaming, overreaming that happens during the construction by hitting in of those temporary drift pins and bolts. That changes in shape and distortion are easily filled by a hot rivet. Nothing will be left unfilled or out of sync, out of coincidence. So that is the idea that they prefer the hot rivet. And these are also HTS rivets because the truss is HTS.
Right. Okay, this is to the latter part of your presentation now. Why were the stiffeners not used to stiffen the web plates of the bottom chord instead of increasing the steel grade to FE 590E?
It's a box section. Okay, Mr. Ganesh, it's a box section. A box section has stiffeners inside. There are intermediate stiffeners inside the box, inside the hollow box, not outside. It's not an I section, but where we have I sections, you can see stiffeners outside the box. Okay, outside on the eye. There are stiffeners which I can't show. I didn't show you, and I can't show you. And in a photograph, I don't have that. But there are stiffeners at regular intervals, intermediate stiffeners, which allow a man to walk through. And at each end, over the nodes, at every node, there is a very robust, thick stiffener, which acts as at the node, as a diaphragm element at the node. So it is fully stiffened. Bottom chord and top chord are fully stiffened inside the hollow sections. Okay. And all I sections, you can see the stiffness.
Okay. During the inspection, what you related, you had shown some cracks.
No, actually, Ganeshekhan's question is different. The buckling that which happens, the plate type buckling that happens, we already have intermediate stiffness inside, as I told you, but they are not going to cater to this very high demand. The whole cantilever action, the whole effect of that cantilever plus bending action and compression due to axial compression and bending compression accumulating at one node complete. And it is not designed to take that. So the only way, and we were not allowed to weld anything on. Now that it is built, we cannot weld anything on. So if you can't weld the stiffener on, and they were unprepared to put further holes because A gross A net, it's a tension element in service. And A gross A net, as you know, in a tension element, if you put in holes additionally in the web, to put in a stiffener there, will violate the tension requirement. So all those situations were there, and we had to then very cleverly, either do this or that. Yes, it is also very clever. It's also very correct. The absolute limit increases to lower the BIHAR limit. That also is corrected and taken care for. The loss of effectiveness is designed, and it's for the first time that has been done in railway. It is designed as a slender member.
Okay. Okay, the next question I will take is by Venugopal Gurugullipalli. It was related with the cracks that you showed during the inspection. So have you placed any Hillman rollers on temporary trusses? I think cracks near knuckle bearing may not happen if Hillman rollers are used temporarily during erection.
No, we didn't use Hillman rollers. This was what was done by the erection design engineers. We didn't suggest Hillman rollers. These knuckle bearings were required because you need a certain amount of rotation. The truss is coming down as it forward launches, it keeps coming down in height. We launch upward trajectory, it comes down and just about makes the bearing at the end. So that is why we had that rotational ability on that specially designed bearings. Mind you, they had argued that it was not required. We had argued that it was required, and thank God it was changed before we launched. Otherwise, we would have had a chaos. One span would have gone into the water straight.
Yeah. Ganasekaran has asked one more question. Were the top bracings, hollow sections, closed at the ends to prevent the moisture ingress?
What? Sorry?
Were the top bracing hollow sections closed at the ends to prevent moisture ingress?
Yes, of course. You mean those cutouts? They are covered.
The cutouts, yeah, whatever cutouts or the hollow sections you have provided.
Open and then they put that spray and all that all over wherever there is some working and all that, because the working before the truss is commissioned, they will spray to get that galvanizing back. It's all galvanized, so we'll get that galvanizing back with the spray system. Wherever there's an infringement or a rust is showing, etc., they will treat it and do it up. Then they will put the lid. A lid will be put, if you like, on all the cutouts. Is put.
One more question from Mohammad Alam. You said that you had designed your joints for 2 times the seismic forces. So he is asking the question.
Not joint. We have designed the seismic restrainers.
The
forward seismic restrainer and the transverse seismic restrainer, longitudinal and transverse.
Okay.
For 2 times the seismic force demanded on the bearing. So once my bearing fails, the capacity design of that bearing for seismic, I have 2 times that ability still in my longitudinal and transverse restrainer.
Okay, so it was misunderstood by him. He understood that the joints were designed, and that is why he raised the question that why the
seismic restrainer. Ma'am, the seismic restrainer where it joins the parent members, all that is designed for 2 times P. The force that arises due to 2 times P being applied where it is held, then it will cause bending in the downstand member, etc. and all that will bend and all that. So that is designed with a 2 P. He is right. The end bottom member that projects in all and the joint at which it is held is all designed for 2 times P.
Okay.
Very correct.
Next question. How much time it took to complete the design?
Oh, it was a never-ending affair. Changes. Railway is not nothing is straight. When you first we started with rights, then there was some incompatibility working for rights. So Madhresh Kumar, the CEO, rescinded rights and appointed us directly, and that increased the rate of the project because whatever the requirements were, we met. And then he also asked us to supervise the project. IRCON asked us then to supervise the project. The contract was then put on us by IRCON rather than by rights and railway. And the IRCON took over, and as an EPC contractor, we then became their prime consultants, as I said, for all those things.
Okay. Ganasekharan has again one more question. Are the railway beams connected to the bottom plan bracings?
Are the
Railway beams connected to bottom plan bracings?
The railway have stringers. They are braced and tied. Yes, they rest on them. No, they are tied on them. They're clamped onto them. No? Onto the stringers. The railway, it will be clamped onto that. Okay.
Right. Let's go to the next one. I think we are done with that. Some comments. Excellent presentation of a marvelous piece of engineering by Dilip Kumar.
Again, Deshpande ma'am, thank you for your kind words. But Deshpande's asked a question at maximum cantilever. Sometimes our design estimate is always considering deflection limit at the erection I'm talking about, that we should come in just at or above the bearings by at least 200-300 millimeters to 20 centimeters, 30 centimeters over the bearing or the packing that we'll have, the packing height that we require. We have to come in over that. So that is the way the buffer block and the deflection and stress analysis will be done for the erection to ensure that we don't sag down and then we have to pull up the truss, we have to jack up the bloody truss from below up. So that becomes a problem sometimes. It does happen, and that largely happens because of being too zealous in the erection speed and work. Sometimes it does happen, and the truss does not come in at the level and line over the bearings on which it should land. And then we have traversing jacks. If it is laterally not in line, we have traversing jacks. We traverse them back into direct position over the bearing laterally, and vertically. Sometimes we lift. We do need to lift, but in this case, we never had a situation where we had to make a bracket on the pier and put jacks there and jack it up. The analysis was very rigorously checked by us, and we changed many of the things. Yes, ma'am. We changed many things in our proof checking of that, and innovations there too.
Okay, one more question I just found related with the answer that you gave. Seismic stopper or the seismic restrainer that you said that it was designed for double force. So now is the substructure also designed for the same?
Yes, the substructure is checked for that. Now, you have to check the point really is the substructure is very robust. What was failing in our case in the seismic condition was the small pedestals. Forget the seismic condition. In the normal case, it could not take. The bearings were becoming too demanding. So the pedestals that were originally provided, if you remember the story, for the single rail line, it was originally constructed, the whole substructure, foundation, everything was constructed with a single railway track of BG loading. We switched to MBG loading, and there is so much reserve in this truss, it can even handle 25.5 ton loading by setting those at 0.8, as I told you, the utilization ratio. There's reserve in the truss to even go up to 25.5 ton loading. This is very unique. I mean, we foresaw all this. That's why we did this.
Yeah. Let's take the last question. It starts with the appreciation. Thank you for the wonderful bridge and your presentation. This bridge is robust, but can you please comment on the laced batten members found in many rail truss bridges? How safe are they compared to this?
I won't say anything. There are many which are designed so, and there is nothing wrong with them. designing a race battle member, you have to do it correctly, right? But here we didn't want to take any chance. No, there were two pressures actually. One was Patna, the existing Patna bridge, road bridge was in very, very bad condition. We needed immediately, strategically, we needed some crossing that was possible, alternate. The road deck was therefore put in by National Highway.
Okay, thank you, Dr. Harshavardhan, for answering this question. Now I'll just want comments from the panelists. If anyone interested, I will ask Mr. V. N. Hegde sir to put some comments. Please unmute yourself, sir. You're not audible.
Venkat, your volume is, yeah, perfect, volume.
Yeah, now it's okay. Yeah.
This was excellent presentation as usual by Dr. Harsha, and he has gone on very meticulously explaining the design concepts, and then he has gone on to explain the construction aspects also, particularly in relation to the design, like how the design has taken care of the construction stage analysis, explaining that the buffer plate as well as this the connection at the top, that has to be there, has been beautifully explained, and in his inimitable style. It's very difficult to imitate Dr. Harsha. I have been knowing him for a long time, and I've heard this presentation earlier also. Excellent. Harsha, I got a couple of questions actually speaking. Like this, these days when you are going for the double-decker bridges like this, top road bridge as well as the railway bridge, normally what people are finding is the K-truss is in the elevation I'm talking about, not in the plan. Found to be more economical, but has any value engineering was done comparing the different kinds of trusses when this was?
Actually, this was a requirement by rights. They wanted to, this is an N-type truss, which is modified by the hanger post situation because of the road deck coming in between.
Yeah. It's a diamond.
Because of that road deck being suddenly put in between at a later stage, the evolution of this, over the years with railway, then this things changed, and the structural action therefore of course changes by this modified N.
Yeah. So that was a given, that you had to go for this,
because of the road deck.
Another thing is, what I understand, it's a simply supported basically spans in the service condition. Then in that case, how this were there long welded rails, or you had a joint?
No. There are expansion joints in the rails at the truss has at the same location as we have in the road deck.
Oh, I see. Multiple expansion joints were there. Similar to even in the deck also. Even in the deck also you have.
The road deck is at the end of the truss, wherever we have the expansion at the end of the truss, that situation. The same is carried above.
Same as they carried this one. Another thing is, in one of the photographs, what I saw is the plan in the plan of the K truss at the top. You had an open end.
It's a tube.
It's a tube. But
tube with a lip. Tube with a plate lip.
Tube with a lid. But did you keep that opening as it is, or covered it?
I think we have left it open because I think it is left open. We would have asked for it to be closed, but I don't know if we will close it with some plate or something.
No. But
the point really there is those are very cheap elements. I mean, I'm least bothered about those elements. They can be easily replaced.
No. My concern is that if the water can accumulate.
Yeah, that's the point. I got that point. Point.
That's the only concern there. Otherwise,
that's a good point. I hope it is sealed, but I'm not sure.
I think you should suggest even now.
Yeah.
It's not sealed to.
You can seal it.
Suggest that might have also the possibility is there.
Yeah.
And fantastic. And another question is that nowadays the railway bridges. This was done when you did it on the basis of the working stress, allowable stress method design. Now, if the same thing has to be done by limit state, you think whether it's going to be more economical, it would have been, or the working stress method is still insisted upon in railways now?
I shouldn't comment
Uh.
because Ravindra is the right person to comment and he's not here.
Ravindra, he has left. He was there for the entire presentation.
The main point is, at that time when we designed this truss, we could not get plates more than 64 thick, for example. And that also they were not going to guarantee us.
Okay.
In the center, my webs are all 64 thick. Bottom chord webs are all 64 thick for many panels. That set my limit. I have 64 plate, I have to innovate, reverse engineer, and what can I do? Because nobody was prepared to give us a plate beyond 64 thick at that time. Today we can get plates 128 thick, also double that. But then they would not roll. We broke heads with everyone. So that set one direct constraint on the project.
Okay.
That was the main constraint for the innovation of the sections and all that. Then, what was the other question, Venkat?
I think that working stress method versus
working. I can't comment. I didn't compare in this particular case. I haven't compared, but let us say one thing: limit state had taken things to the limit, and with railway, they never want anything taken to its limit. They want a lot of reserve because the railway axle loads keep on increasing.
Yeah.
Already 25.5 ton type loading is flying on this bridge. Though the design criteria is kg loading. This is the way it is. And you never know the axle load 2 tracks below, 2 road below. You already know that from the time it was there, we have added 2.5 tons or something. We have increased that congestion factor for DIGHA in our road deck loading.
Yes.
So those are also reserves, right? So the truss has in its structural action, whether it's road or rail, it has to take a common, after all, it goes back to the bearings and the whole truss acts as a complete unit.
Yeah.
Whatever be the live loading. So therefore, I think this reserve I think this reserve that is already inherent in working stress approach is a good thing to have. It is in fact, critical structures like this, railway is always reluctant to shift away from working stress approach because of that, because of the known that you will have some reserve. You know that you will have some reserve in any case in the structure.
Yeah, excellent presentation, Harsha, and congratulations on that. And hopefully you'll come out with some more wonderful works like this in future.
Thanks.
Thank you, Mr. Hegde. Yeah, I would like to ask Mr. Vinay Pandey to put some comments.
Thank you, Dr. Harsha. It was really a nice presentation. Particularly, it was learning for me with regard to safety innovations, which was done on the fuse yield point, which you explained. And I understand that the audience and attendees must have got some insight. And they will also try to adopt such innovation design in future and create sustainable structure for the country. I thank you once again and thank all attendees to join this webinar. Thank you.
Okay, thank you once again to everybody, and I just hand over now back to the coordinator.
Thank you, ma'am.
Yeah, thank you.
To all honorable dignitaries, it's my privilege to have been asked to propose a vote of thanks for our 6 months webinar series on Steel Bridges Day 5, sponsored by JSW Steel Limited. I, on behalf of IIBE, extend a very hearty vote of thanks to all members and non-members for gracing us with your presence and sharing with us your valuable feedback and suggestions. Firstly, I would like to thank our Director General, Engineer D.G. Diwati, for always providing us with a vision for the future of IIBE, our President, Engineer Vinay Gupta, for constantly guiding, motivating, and inspiring us to achieve the vision. I would like to thank our newly appointed President, Dr. Vishal Thomre, for being a strong support of IIBE, our Honorary Secretary, Dr. Gopal Rai, for always guide us with his humorous side, our Honorary Secretary, Engineer Swapnil Joshi, for always managing the platform. I would like to thank our today's speaker, Dr. Harshavardhan Subbarao, for his enlightening and entertaining presentation and for sharing his valuable knowledge in this platform. I would like to thank our today's moderator, Dr. Jyoti Busari, for managing the webinar on this forum. I would like to thank to all our eminent executive committee members for their valuable presence and support. I would like to thank to Engineer Deepika Singh, coordinator of IIBE, for always helping and managing the events of IIBE. Last but not the least, Mr. Hozappa for all his IT support. Also to all the participants for always coming in huge number to make this webinar a great success. Thank you. With the permission, I would like to close the session. Thank you.
Thank you.
Thank you all. Thank you. Have a pleasant weekend and a lovely evening. Bye now.
Thank you, sir.
Thank you. Thank you.